I must apologize for not speaking Spanish too, and I'll try not to be repetitive because many of the concepts I have in my presentation have been already mentioned by the previous presenters. And so here I'm presenting the results of our research group from University of Maryland, and also of our, we are working in collaboration with scientists from Woods Hole Research Center, and also with Steven Stayman from SUNY. He was already mentioned today several times. And so it's more like the illustration of the concepts Pontus was talking about earlier, like how we implement these good practices, or at least try to implement them. And so we are focusing on the accuracy assessment of the activity data. And it's important because if you're even using the simple stratify and multiply approach to assess your carbon stocks and carbon stock change, your estimates can be improved significantly by applying statistical adjustment for errors to the activity data. But if you're using already published data sets, accuracy information often is not published, or at least not fully published. So you have to do this accuracy assessment, error adjustment yourself. And also, it's complicated by the fact that for many countries, there is no or very little ground information available, and this is the case of the Democratic Republic of the Congo, one of the countries we are working on. In this country, due to the political unrest and recent conflicts, there are not many roads, and actually some people just moved to the forest away from roads that bring war, and that's why forest cover change in this country is also very small scale, influenced by these socioeconomic processes. So here's the data set we're using for the DRC project. It was already published, DRC Facet Atlas and DRC Wetland Map. Facet Atlas was produced using 60-meter resolution Lancet-based composites for 2000 and 2002. And it presented three major forest cover classes: primary forest, secondary forests, and woodlands, and forest cover change within these classes between 2000 and 2010. But for this analysis, we've overlaid this map with a published wetland map of the same resolution to get 6 forest cover classes: terra firma or dryland, and wetland, primary, secondary forests, and woodlands. So my analysis further will be based on these 6 forest classes. So here how the facet data overlaid with the wetland map look. Here's the area of dense forest, green and dark green there, dryland and wetland primary forest. Here's some secondary forest and forest cover loss within them. Here's the woodland area, probably cannot see really well here in the projector. And just a few words about the carbon data we use. Alexandra Bacchini will present this part of the work later, because we're using his glass estimated biomass. Here we were just treating this glass estimate biomass data, more than 400,000 estimates for the DRC as kind of a substitute for national forest inventory data. Of course, if you have better data, if you have already NFI established in the country, it's better. So we were just averaging this data over our forest cover classes to get mean per class mean carbon density values, and here these values for our target classes, and here just provided a brief comparison of this data with different published estimates. In our data are in orange, the data we were using in this study. You see they correspond pretty well with other published maps, except of the Kinderman one that is based on FAO statistics. So now to the main part of this research project, to the error adjustment of activity data. So Pontus already covered this idea. Basically, we wanted to exclude all commission errors and include all emitted loss to the final forest cover loss area estimate for the DRC. For that, we used stratified random sampling, and our forest classes were our primary strata, but we also had substrata within these classes that were forest cover loss and no forest cover loss. But we've also added an additional probable loss strata to our analysis. That was just based on our understanding of the product we are working with. So FACET is a national scale product, and we believed it was more conservative, so emitted more forest cover loss than committed. So based on that assumption, we've picked this sampling design. And again, I won't go into detail about sampling design choice. Miguel had it covered pretty well, the whole slide devoted to that 2009 Steve Stamen's paper on the choice of sampling design. I just want to say that because we accounted for this, tried to account for this immediate loss using this probable loss strata, we picked the allocation of samples among the loss substrata that was closer to equal. That helped us to account for commission errors also, not to miss committed errors of commission. So finally we had 1,000 samples within this six strata, and we were using original 30-meter Lancet imagery, all imagery available through the USGS archives. And just to remind you, FACET data is 60 meters, so our reference data was better, had better resolution. And we also used all available very high resolution data from Google Earth and from NGA archives. And here again, as all presenters, our methodology is based on the Cochrane 1977 work, but the difference here is that our validation strata don't match our map strata, so it's kind of like a kind of specific case, and Steven Stamen is right now publishing the paper devoted to this case when validation strata don't match map strata. It's just an adjustment of the method, nothing really super different. Here again to illustrate the idea that we had the 60-meter map pixel, it is given in red box here in this picture, and 30-meter Landsat validation data, and also some high resolution data. You cannot see really well, but here in this image you can see really like a bare ground with the line stems on the ground when you check it through Google Earth. And so this difference between map resolution and reference data resolution allowed us to perform two levels of error assessment. So it was a map scale estimate and subgrid estimate, so we called it. So in the map scale estimate, we accounted only for the pixels that were 60-meter map pixels that were completely misclassified. So it was like if more than 75% of this pixel was lost according to our reference data, but we classified it as no loss, and the opposite. So for example, this example for the map scale estimate wouldn't be considered as omitted forest cover loss. But for the subgrid estimate, the first map scale estimate kind of accounts only for the classification errors that were in the product we are assessing in the FACET product. But another subgrid estimate allowed us to account for the errors due to the different resolution of the map and reference data, to the fact that we can see more smaller scale change in our reference data that the map was able to show. Oh, I can see the colors here, but here the map scale subgrid and original estimates, and just the pixels from the map counted and multiplied by the area. And you can see that just adjustment for the classification error and map scale estimate brought for the main dryland classes, primary, secondary, forest, and woodlands, brought extra like 30% of forest cover loss. So our assumption that FACET product was conservative was actually correct for these bigger classes. But for the smaller classes that were more specially scattered, FACET actually committed more loss than it emitted. But you can see that if with the subgrid assessment, when we counted for all the smaller scale change FACET wasn't able to see, we estimate the estimated area of change is almost twice bigger than the what we're just see in the map. That might not be, these differences between error-adjusted and map estimates maybe not that huge for different landscapes, but for the DRC, where they told you a lot of forest cover change associated with a slash and burn agriculture, people just living in the forest, cultivating their small plots, it brought a lot of extra changes we were not able to see in the past. And just to note here that all these estimates are really dependent on sampling design and number of samples. For example, in primary forests, this 20% of loss area in the map scale estimate was from one loss sample that was emitted out of 353 samples in this strata. I wish I had like more time and resources to maybe do several realizations of this, validation exercise, and just to see how different they would be. Here's just a graph illustrating our map scale subgrid estimate and map estimate of forest cover loss. And you can see that the majority of loss in the DRC was found in secondary forest. That actually raises the issue of reference forest state in the forest cover loss and carbon stock change estimates. So, of course, it's the most important focus area for many projects, and RED project is primary forest, but this whole huge amount of dynamics that is happening in secondary forest should also be accounted for. Whoop. This was covered by Osvaldo yesterday. It's just a standard IPCC methodology that we use to combine uncertainties coming from biomass data. Okay, here it's shifted a little bit. And from activity data, and also we used addition and subtraction approach to get a total uncertainty for the DRC, because we assessed uncertainties for these different forest cover types. But it's pretty standard. It's all in the IPCC 2006 guidelines. Here again, colors are not that great, but I just wanted to compare our estimates with the already published ones. And you can see that, for example, this one, the estimate of Ernst et al., it was sample-based estimate, also using the 30-meter resolution, Lancet resolution data. So you would think it should be closer to our subgrid estimate than to the map scale estimate. But the thing is that here's the difference in methodological approaches. They use the minimal sampling unit of 1 hectare to assess accuracy of the product, while we were working on the pixel level. So maybe the difference between these estimates is coming from that. Also, you can see that, for example, estimate of Hansen et al. 2010, that was based on modest stratification, and then within this modest high and low loss strata, it was Lancet-based, sample-based estimate. It was highly uncertain in the DRC and in Central Africa in general, because it was in the low change modest strata, because modest just couldn't just catch all these smaller scale disturbances. And so when we were moving to 60 meter and then to 30 meter assessments, we were kind of like getting more and more forest cover loss in this environment, and also we're reducing uncertainty of the estimate. See, with the modest certification, it was huge. And these things are important to have in mind when you're comparing gross carbon loss estimates from the literature. For example, Harris et al. Estimate that was published in Science was based on Manhansen's modest and Lancet-based estimate, and also on Sarchi's carbon density map. And you see that if you just look at this number, they show it in the main table in the science paper without the plus or minus. You can see, wow, you can think, wow, it's so different from our estimates. But if you think about the margin of uncertainty this forest cover loss estimate had in the first place, you think that these estimates are not that radically different. So my message here is that just like look attentively on the accuracy information of the data you're using, and report all of it as in as much detail as you can. Now here, just to visualize this map scale and subgrid estimates, you see that all the differences between these estimates are mostly in the change areas. The paper has been recently published based on this research project, and it's an open access. It's published in an open access journal, and we provided a really detailed step-by-step description of the methodology we use, so anybody who's working on the similar type of research in any country of the world can easily access it without any subscription to the journals or anything like that. And the second example is a Peruvian project. It's only starting, so I don't have I have only preliminary results for this project. But this is again the example of the sampling design choice that Pontus was talking about. Here we used cluster sampling not because it was like the best thing you could possibly think of, but just because we had limited funds to purchase rapid eye scenes. We could buy only 30. We had funds for only 30 scenes, and this is the minimum size of the rapid eye image you can buy. So the size of the block was also kind of not defined by us. And so at the first level of this sampling, we had this 30 rapid eye blocks, and then we threw 100 random points within each block. And we also we are working with the force cover loss product that was created at the national level by national specialists. We're collaborating with Ministry of Environment of Peru for this project. So we got this force cover loss 30-meter product, also based on Lancet composites that they produced, and we stratified the area based on the percent of mapped force cover loss within this 12 by 12 kilometer block. So we had low and high change stratum, and within high change stratum only 9 blocks, but within low change stratum 21 blocks. Oop. And so just to illustrate this process once again, so this is a force cover loss mask from 2000 to 2011. This is a humitropics mask. Again, we were all, working only within this mask that was also provided by the Ministry of Environment of Peru. Yeah. And so we were using only the 12 by 12 kilometer blocks that had more than 40% of humitropics mask within them. And here just the percent of forest cover loss overlaid. So in dark, I'm not sure, I don't remember. I think in dark it's high loss probability, in white is low loss density. And so here in small red boxes, there are our 30 rapid eye blocks. And this is how the block looks, just with 100 random points thrown within this block. And just to illustrate the advantage of using rapid eye here. So here's the day 1 Lancet image with the sample blocks that are the size of 1 pixel. And here is the 2011 Lancet image. So for some of these blocks, you can say tell for sure that they're within the areas of no change. But some of the blocks are not that easy to identify using 30-meter data. So here, rapid eye helps a lot, and you can see that this block was actually within the changed area with forest cover loss, and this wasn't. And so, as I already mentioned, this is just we're still working on the project, so these are just preliminary results. But you can see that for Peru as well, this area adjustment of the area of loss brought extra loss that was missed in the original forest cover loss classification.
Secretaría de Medio Ambiente y Recursos Naturales.